Welcome to Pre-Calculus, Unit P, Lesson P3, Radicals and Rational Exponents. In this lesson, we are going to go over radicals or roots and also rational exponents. But in this first part, we're going to review our square roots and their properties. First off, what we want to be able to do is evaluate square roots. Remember, a square root is any number that times itself gives us the number inside of the radical. For example, in this first one, if we're trying to find the square root of 81, we will try to think of a number that times itself would give us 81. In this case, that would be 9, because 9 times 9 is 81. In our second example, we had the negative square root of 9. In this case, since the negative is on the outside, we can go ahead and evaluate the square root of 9, which would be, in this case, 3, because the square root of 9 is 3, because 3 times 3 is 9. On our third example, we can also go ahead and take the square root of a fraction, by, in this case, taking the square root of both the numerator and the denominator. In this case, taking the square root of 1, making it 1, and the square root of 25 being 5. And this gives us an answer of 1/5. On the fourth example here, when we're trying to evaluate square roots, we want to treat the radical like a set of parentheses. So using our order of operations, we need to do what's inside the radical here first. In this case, adding together 36 and 64, making this the square root of 100. And so if we go ahead and evaluate the square root of 100, well, 10 times 10 is 100. So we can go ahead and take the square root and get 10. On the fifth example here, you'll notice that the addition sign is outside the two radicals, so we need to evaluate the two radicals first. Thus, we take the square root of 36, we get 6, and the square root of 64 and get 8. And finally, we're going to add those together to get 14. One of our very first rules that we need to know when we're working with our radicals is the product rule, or what's going to happen when we are multiplying two radicals together. In this case, notice that both those radicals need to be non-negative real numbers. Like I've already said, we cannot take the square root of a negative number. So in this case, what we're doing, if we have a product on the inside of the radical, we can go ahead and split those apart, or vice versa. So like for example, if we were to take the square root of 2 times the square root of 5, we could go ahead and bring those both inside the same radical and get 2 times 5, or square root of 10. We could also go the other way and break 10 apart into 2 times 5 if that would help us reduce. So let's practice this. In this case, on the very first one here, we want to simplify square root of 75. Notice there's no number that times itself automatically gives us 75. And so what we're going to use here is use our perfect squares. By perfect squares, I'm talking about those roots that come out nicely. For example, the square root of 4 is 2. Square root of 9 is 3. Square root of 16 is 4, and so on. So we need to think about, in 75, which perfect square could go into 75. Well, in this case, we can split 75 into 25, which is a perfect square, times 3. And using the product rule, we can split that apart into the square root of 25 times the square root of 3. And so if we do that, we can reduce the square root of 25 to 5 and get our answer of 5 square root 3. Notice our final answer has no perfect squares left in the radical. If we go to the next one, where we're trying to simplify 5 times square root of 27. Well, notice we're going to have that 5 there, but we can split the 27 into the perfect square of 9 times 3. And so using the product rule, we can break that apart into 5 times the square root of 9 times the square root of 3. Then if we simplify that square root of 9, that'll give us 5 times 3, which would, in this case, give us 15 square root 3. In this last example, notice we're going to be going the other way. We already have a product here, square root of 5x times square root of 10x. Neither the 5 nor the 10 have a perfect square that we can take out. So what we're going to do first is go ahead and multiply those together, giving us 5x times 10x, which will give us the square root of 50x squared. This is what we want to simplify, because we can break that down into the perfect square of 25 times the square root of 2 times the square root of x squared, which if we break down the 25 gives us 5, break down the square root of x squared giving us x, and then bring down the square root 2. Remember, we can't take the square root of variables. In this case, the square and the square root are just going to cancel each other out, leaving us that final answer. Well, just like product rules can go both ways, the same thing with quotients. So if we're taking the square root of a fraction, or in this case, a quotient, we can go ahead and split that up into the square root of the numerator divided by the square root of the denominator, and vice versa. So for example, if we're trying to take the square root of 25/16, this would be the same thing as the square root of 25 over the square root of 16. Or if we reduce each of those, 5 over 4. Going the other way, notice in the denominator is square root of 2x. We cannot break that down any, so we're going to work backwards and bring both the numerator and the denominator inside the same square root, giving us 150x cubed over 2x, which we can reduce to, in this case, 2 goes into 150 75 times, so we get 75, and if we cross out 1x in the denominator, leaves us with 2 on top, and giving us x squared. So here then, we can go ahead and break down the square root of 75x squared using our perfect squares, or in this case, square root of 25, times square root of 3 times x squared, which if we simplify that, gives us 5x square root 3. That's how we multiply and divide radicals. But in the case of adding and subtracting, just like with variables, and you can only combine like variables, we can only add and subtract like radicals. For example, square root of 2 plus 4 square root of 2 leaves us with a total of 5 square root 2's. If our bases don't match, like in the case of square root 3 plus square root 5, we can't combine those at all. So that right there is going to be our final answer, and that's how we are going to write it. So we have to have those like radicals. So for example, if we're trying to add 8 square root 13 plus 9 square root 13, well, since they have the same radical, we can go ahead and combine those numbers on the outside, in this case, the 8 and the 9, making this a total of 17 square root 13. Same thing with subtraction. In this case, we have like bases of square root 17x, and we have our coefficients out on the front of a 1, even so remember if nothing's out there, there's still a 1, in this case, minus that 20 square root 17x. So we can subtract the 1 from 1 minus 20, giving us negative 19 square root 17x. Now, in our next example here, we have 6 square root 8 plus square root 32 minus 5 square root 50. If we look at this right now, we notice that none of the bases are the same. Or sorry, bases of the radicals are the same. So what we want to do first is simplify those by breaking them down using those perfect squares. For example, in this first one here, we can break down that square root of 8 into square root 6 times square root 4 times square root 2. Square root 32 breaks down to square root 16 times square root 2. And the minus 5, we can break down that square root 50 into 25 times 2, leaving us with those that we can go ahead and then simplify. So for example, in that first one there, if we go ahead and take the square root of 4, we get 6 times the 2 times that square root 2. Break down the square root of 16, giving us 4 times square root 2. And then the square root of 25 is 5, and so we get that 5 times 5 there. Simplifying that multiplication, we're going to get 12 square root 2 plus the 4 square root 2 minus 25 square root 2. Now notice how all the bases are square root 2, so we can go ahead and combine those coefficients. In this case, doing 12 plus 4 minus 25 square root 2, which would give us a total of negative 9 square root 2. Rationalizing the denominator, the process of getting rid of the radical in the denominator. To have a fully simplified radical expression, we cannot have a radical in the denominator. So this is the process of getting rid of it. This is done by multiplying the numerator and the denominator by the radical that is in the denominator. So to illustrate that, let's try this first example. Oh, and actually back up. In this case, in some cases, when it's just not one radical in the denominator, in this case where there's radical expressions that involve the sum and difference of the same two terms, this is when we're going to use conjugates. For example, if we have the square root of a plus the square root of b, well then the conjugate of that would be the square root of a minus b. It's just flipping the sign. We are going to use the conjugates to get rid and help us rationalize the denominator where there's more than two terms with square roots. In this case, instead of just multiplying by the square root that's in the denominator, we need to multiply both the numerator and the denominator by the conjugate. So let's practice this. Notice in this first example there is just one term in the denominator, a square root 3. So what we're going to do here is we're going to get rid of that square root in the denominator by multiplying by square root 3 in the numerator and square root 3 in the denominator. Just like fractions, we're going to multiply across. So on top we'll get that 5 square root 3, but then on the denominator we can use our product rule to bring those together, giving us a square root 3 times 3, which would give us square root 9 in the denominator, but we know that's going to simplify to just 3. So our final answer is 5 square root 3 over 3. Notice now that the radical is in the numerator, which is okay. As long as it's not in the denominator, we're doing just fine. If we look at our next example, in this case we notice we have two terms in the denominator. We have a 4 plus square root 5. In this case, we can't just multiply both the numerator and the denominator by the square root of 5, since it is two terms. This is the case we're going to have to use conjugates. Very first thing we're going to do here is put those denominators in this case parentheses. And then we're going to multiply both the numerator and the denominator by the conjugate. Notice all that does to do that is just going to be flipping the sign of what was in the denominator. In this case, 4 minus square root 5. From here, what we're going to do is we're going to multiply across just like we did in the last example. So we're going to go ahead and distribute the 8 to the 4, giving us 32. And then multiply it times the square root of 5, giving us just 8 square root of 5. In the denominator here, though, since we have two term, or in this case binomials, it's going to be like we're kind of foiling here in the denominator, or just distributing the 4 to both terms in our conjugate and the square root of 5 to both in the conjugate. So if we take the 4 times 4, we get 16. 4 times the negative square root of 5 gives us a negative 4 square root of 5. Positive square root of 5 times 4 gives a positive 4 square root of 5. And then finally, if we take the square root of 5 times the negative square root of 5, gives us a minus square root of 25. Notice those two middle terms, though, are the exact same thing, just opposite signs, so they're going to cancel each other out. So we actually get here on top 32 minus 8 square root of 5. In the denominator, we can take that 16 minus the square root of 25, which is just 5, which gives us a numerator of 32 minus that 8 square root of 5 all over a denominator of 11. Again, the denominator no longer contains a radical, and so this is a properly simplified radical expression. Please pause here if you need to go back and look at any of these examples. Feel free to pause, and then we'll go ahead and move on to part 2.